I get to follow the guy with the giveaways. That's good. All right. Well, it's great to be back here. It's good to be out here. I want to go stand in the middle of all this hardware. This is kind of cool. Last year, Calista said, we had a little table with about 15 pieces of hardware. I like it here. This is good. This is great progress. Good to be at the summit. I appreciate you all coming. My name is Brad McCredie. I guess in a lot of ways you could say I'm the guy that started this idea as we were evolving our power systems. I'm going to talk to you about something today that's really specific. I'm going to talk about the power roadmap. Those aren't my charts. I'm going to talk to you about the TSC work groups and accomplishments. I just studied up on this. I'm going to do a reload here maybe and try the next ones here. But what I'm going to talk about is there we go. This looks good. Let's see how this one goes. I'm going to talk about the roadmap for for power systems, and I thought I'd start by that with a little retrospective. All right. Now all we need is a page down key. All right, Jerry, where are you? I'll get my TA back there. He's really good at hitting the page down key. Trained him for about a year. Okay, we're ready to go here? All right, here we go. Oh, now we got to go backwards. Here we go. All right. So this is where I was going to start. I wanted to talk a little bit about where we've been, because if you look at where we're going and how the big discontinuities are hitting, I think it's instructive to hit a little bit where we've been. Kind of look at it through one disruption we've been through already. As you see here, this is really the whole history of power chips that we've developed over the years. Started back in 1990. You could see our early days of power systems. It was a very traumatic first 10 years, in that's when we went through the bipolar to CMOS transition. That's what actually put Unix on the map, right? If you look at this lower left-hand corner, I'll never forget when I actually first met a power computer. It was at the University of Illinois in the early 90s. And I was running systems on McCredie, and I was running systems on power systems, running programs on power systems. And actually at that point, right, the McCredie, the bipolar machine, they actually told me I ran up about a $5 million bill of McCredie time. Because it was and I was just using unused minutes on the McCredie. And then we got a power system, and I got a quarter of the scalar speed on this little $30,000 box running on a CMOS processor. And of course, that's what drove a huge disruption in the industry, is the disruption from bipolar to CMOS, which was synonymous with Unix systems. And that was great. Power grew with that. And we got up to the point here in about 2000, which was a bit of a discontinuity to us. You can see we started lots and lots of power projects. We had a unique whole chip family just to do our I-series systems that ran iOS. We had, as you may recall, in the Apple products, the Somerset projects. That's the lower left ones, and PCs. And then we had our workstations, which were in the middle. We got to 2000, and it was a moment where we said, hey, we're not doing so hot. If you actually looked at the Unix market share, we were a distant third. We had about a 9% share. Sun and HP had a 25-ish to 30% share, each of them. And the boss came down and said, what are you guys going to do about it? You can see what we did. We took all the projects, converted it to one, started Power 4, bet the whole farm on it, and we started a new era in power systems. It's a great worst to first story. We've gone from a 9% share to a 60% market share in Unix. Built some great processors. Power 4 was a hugely innovative processor, first processor that had a glueless fabric, first processor that was a server processor that had multiple cores on it. Started that trend. First distributed memory controller that now everybody is using in all their microprocessors, all there in Power 4. And over that period, we went and did the pretty good sweep of the Unix marketplace, and that takes us up to Power 8. You can sit there and look at a couple of the interesting things that happened in the ecosystem in that time, right? The whole time we were developing Power 4, everything that showed us on competitive analysis, we were going to be a distant third. Behind Itanium and Spark, a strong distant third. But what was the hallmark of going from worst to first? It actually was execution back then. We actually executed every one of those processors right on schedule. When we finished Power 4, an analyst, Nathan Brookwood, came to me and said, hey, that was the first processor I've seen that did number 1 in spec int and number 1 in spec float. How the heck did you guys do it? Well, Itanium and Spark, Ultra Spark 5 were supposed to beat us, and they didn't show up. The Merced chip never shipped. That was supposed to beat us pretty handily, and the Ultra Spark 5 went to hardware and never shipped. So that's what we did all the way through that period. But now, we're sitting here with a 60+% market share with these processors in the Unix space. But we're going to enter a new world, right? There's a lot of disruptions coming again, just like the ones that led up to the bipolar to CMOS disruption. Once again, technology's not scaling. Everybody's given the Moore's Law discussion. It's not there. Huge disruption. Second thing that's happening is consumption and development is happening in a much, much different way. It's open now. It's an open development and open consumption model. And that also changes what you're going to do. And those things, all those, you can go on with the discontinuities, but all those discontinuities have led to the microprocessor roadmaps are vastly different than they were here. Here, you also note, in just about everywhere, every box on here, there's no two boxes that ever have a microprocessor in the same technology. The technology cadence always drove the microprocessor development. So this is, from here over, this is the new power microprocessor roadmap. And then you can see now that it reflects these changes and these discontinuities in the industry that are taking place. I showed a little bit of the left side here. That's Power 6 and Power 7. You can see that, again, every square on there is driven by a technology. Every square on there, we go from one technology to another, and we do a very classic new technology, a bump, a new technology, a bump. A new architecture, a bump, new technology, a bump. Now you come over here to the right side, and we're starting this new era of power systems, the OpenPOWER era. Now you can see things are very, very different. So now we've introduced Power 8 in 22 nanometer. Everybody should know and love that. That's been out there since 2013, 14. We have Power 8 with NVLink. We'll talk about that. That processor's coming out. But that is in the same technology with the new advanced accelerator bus. You go in here and you look at our plans for Power 9. We have firm plans for at least 2 processors in the same technology with vastly different architectures and the targeting different markets. And then we go on, and we may even do more. I won't say that the final chapter is written on that. And then we have the yellow box over there, which is the open world. We will have partner-driven chips in these technologies as well, based off the Power 8 and Power 9 architecture. So now that's our open ecosystem starting to kick in. And then we'll start it over again with Power 10. So this is the new way that a roadmap will be looking in the new open, in a new world that's in a post-Moore's Law scaling world. And I'll talk a little bit about each one of these. But these changes will have a big impact on the industry. They're having a big impact on our power ecosystem. Let's take a look at Power 8. So Power 8, most of the stuff on the left here, everybody knows it's a 12-core chip with 96 threads, the most highly threaded chip in the industry for servers. We have our very, very advanced differentiated memory bus, a couple hundred microseconds, megabytes per second of a memory bus bandwidth capability. And then we also have, of course, our CAPI PCI attach. One of the things I wanted to draw attention to is and we talked, Jeff talked about this, is, now we've taken all these buses on here that are highlighted on the chart here, and we've opened them up. And we're building ecosystems around those buses. So, when I first started OpenPOWER and was sharing it with a lot of our partners, and I often tell the story that, everybody that came to me was going to become a microprocessor designer. And I just smiled and said, great, you should all be microprocessor designers. But microprocessor design is a very expensive and a very, very, very time-consuming and hard thing to do. But what we've found in OpenPOWER is that opening up the buses has a bigger impact on the industry than even really letting everybody design. Of course, I'm still going to let everybody design that wants to design micros with us. But what we've really found is lots of the innovation is taking place around the buses. One of the things that we have up here on this stage, I think I see it over there, is we also have up here something I'm really excited about, I want to draw people's attention to, is we opened up the memory bus, as Jeff pointed out. But we actually had the first functioning server-class memory demo going on out at the OpenPOWER Pavilion booth. That's a first in the industry. And that's going to be the first of what I think is going to be a very strong and disruptive trend in the industry, where we got the MRAMs from Everspin actually running on a functioning computer, I think they're running a distributed file system. The guys can correct me if I'm wrong. But it's a 15 times improvement of whether you do like an NVDIMM or some kind of a non-volatile DIMM, and we don't have any of the overhead that is on this system now, where we're actually copying stuff out of a memory buffer, moving it to a flash, and moving it back. But that's a trend that you're going to see a lot of, because all the things that we talk about disrupting Moore's Law and disrupting the microprocessor development, the truth is it's hitting DRAM just as hard, and it's having just as big of an impact on our industry as the microprocessors tail down. So that's a cool thing we got going. We got a lot more of that going on. The card that we built is designed to take lots of memories from lots of suppliers, and there's a lot of activity going on in that space. The other thing, of course, that you've heard a fair amount about, I got it highlighted on here, is our CAPI environment. Up here, we have over 6 pieces of hardware developed that is targeting CAPI. We got over 20 CAPI solutions, because solutions are the things that are going to have the biggest impact. And they go across a broad range of industries and workloads. But, this is now, again, I think you're going to see more and more of this in the industry. But this is the first, again, coherent attached to a processor, so you can get all the benefit of participating in all of that hardware coherency and all of that hardware integration on a processor, but do it in an I/O card, attached to it, get great performance. It's the way you can do acceleration. As I often tell people, I no longer have to tell anybody anymore that, hey, acceleration's coming, you got to think about acceleration. Now, really, people are only talking to me about what is the way to go and do acceleration. This CAPI is a great way to go and get great performance, short programming, and easy integration into a processor without becoming a processor designer. So, this is the stuff that we have on Power 8. We want to see a lot of people grab this technology and run with it. And this is something that our marketing team for OpenPOWER has come up with. This is an OpenPOWER challenge. And this is a place where we're giving everybody access to the technology and, giving them some challenges here. The first one is optimized for the Power Platform challenge. And that is one where you go and you basically do a port, and compete against your first port. How much performance improvement can you get after you do your first port? Do some tuning, throw some accelerators in there. What can you do? That's the first challenge. And the second one's a Spark challenge. I think you guys can picture that. Deep neural network. How fast and how well can you recognize pictures? So this is something that we're inviting people to participate in. I was talking to Adel. Where's he at? There he is over here. He told me we haven't opened up the website yet, but we already got 10 contestants in there just by word of mouth. So I think we're going to get good response to this and a lot of competition. Adel says he's given away $16,998 worth of prizes in this competition. I think it's a great number. I was going to offer right here on stage to give you $2 and make it $17,000. But yeah, I thought I'd do better than that. So one of the, you can see the competition that we're going to give out the awards at Supercomputing in 2016. So, for anybody that wants to participate in this, I decided I'd make it as a live offer. I'm not a lot of fun to go out to dinner with, but Adel's fun. He's in marketing, and marketing guys are fun. So we'll take the top 2 winners out to dinner at Supercomputing. You and I will do that. So we'll get it up to about an $18,000 prize, and it'll be a lot of fun. Looking forward to meeting these people. So this will be good, and it gives everybody access to the Power 8 technology. Go off. Let's do something good. Let's start leveraging the architecture. It's open now. Okay, it's open now, so you can actually sign up. All right, good stuff, Adel. All right, so The next thing here, this is our Power 8 next round. So this is now Power 8 with the NVLink. We put the NVLink onto the processor. This is going to be a disruptive technology. We got a lot of pull on this technology. When you start attaching the GPU to the CPU, over 160 gigabytes plus, and each total bidirectional bandwidth. I got to learn to use Jensen speak. Usually we call it an 80 gigabyte per second bidirectional bus, but he likes the bigger number. So we go 160, but it's bidirectional. So we get 160 both ways, counting both ways. We got three systems up here already. Developed that leverage this technology. Zoom and Inventec both have planars that are NVLink optimized with Power 8 with NVLink. And we have our IBM system. We call it Minsky. How many people know who Minsky is? Well, it's a good crowd. All right. I love it. Yeah, so you could probably attribute him. He founded the AI lab at MIT, and you could attribute him with inventing the deep neural network. So that's what Minsky stands for, or that's the guy's name. This technology, like I said, is going to have a good disruptive effect on the industry. We got a lot of pull on this. As a matter of fact, we got a lot of people wanting access to it. So NVIDIA and IBM have agreed to partner together, and we're actually going to take the first of our Minsky systems and put them in one spot and create an NVLink accelerator lab and start introducing people to this technology, get them brought in early. We got this email address right here for those of you wanting to get access to it. Start sending us your proposals. We're anticipating, we're going to have to do a little bit of time slicing and everything to get everybody going on this technology. So, but we want to give everybody access. We want to teach you how to leverage it. We want to put our experts next to you and get this stuff adopted quickly. This is going to be a disruptive technology that's going to enable people to do things that they just couldn't do before with NVLink. So our next chip, so this is your first look at Power 9. This will be the first time that Power 9's been shown. Just doing a quick preview of it, because my next partners from Google and Rackspace are going to talk about building computers out of this. So I just want to introduce this to the team here. But this is Power 9. We've got 24 cores here. We're going to keep doing, our EDRAM differentiation with our huge low latency EDRAM caches. We're going to keep doing our high performance, high bandwidth memory. Again, we're now planning for deployments into hyperscale data centers. So you can see this particular system doesn't use memory buffers, but I got another one right behind it that will leverage the memory buffers and that memory buffer technology. And this will be the first of our chips in the Power 9 family. The thing I also want to draw your attention to is look at the number of accelerator buses. We started the trend with the accelerator buses with CAPI. We've built on it with NVLink. We're keeping those. We're bringing out another one. We got another high-performance open accelerator bus. I'm going to talk more about that as time goes along. But the message here is that's going to be the way of the future of computing, integration with accelerators, a lot of and sophisticated attach of accelerators. And these accelerators are going to go and do even more things in a more disruptive way in the industry. And that's a big piece of our strategy with Power 9. So that's a first look at Power 9, and we're looking forward to a lot of good stuff with this stuff in the second half of next year. So just to wrap up a little bit and emphasize a few points. Roadmaps are denser. Our roadmap is denser. I think the world's roadmaps are going to become denser because roadmaps are going to become design-driven, not technology-driven. Technologies used to pace these things out. We had that technology cadence. We all know it so well. There'd be something new every 2 years. And the truth is, what we used to do is we used to fill up design work to meet the technology deadline. Okay, we got 2 years of next technology. How much stuff can we cram in there? Now, we're going to be design-driven. We're going to be saying, I got to get this done. I need this new bus. I'm going to put this new definition in this bus. I need this new feature or function, this new accelerator on chip. I'm going to put that in there. We're going to drive our designs to go deliver that. It's a big change, big change. We'll have more teams developing because it's now an open technology. We have people around the world developing on power technology. That's going to be a big change. That will dense up the roadmap as well. Still going to drive for performance and cost performance leadership. Nothing new there. What What we need to deploy these things into these large internet scale data centers is cost performance leadership. No debate on that. Still driving that. We're optimizing on that technology. Furthermore, accelerator attach. I don't think that's a debate. We have a lead in that technology right now. We're going to build on that lead. We're going to add more buses, more features, more capability so that people that as they innovate new things to accelerate these systems, we're going to let them attach to our systems. You can see that our roadmap now is expanded in our strategy to comprehend both enterprise and hyperscale data centers. And then the bottom line, of course, is we're making all of these technologies available to our OpenPOWER partners. These are open technologies. So thank you very much. I appreciate you paying attention. It's great to be out here at the summit. I'll be around for the rest of the day. Love to talk to anybody that wants to talk about what we're doing with just the roadmap here. You know, there's an equally rich roadmap that we have around systems and an equally rich roadmap we have around a firmware strategy, and we can also be sharing those with you guys as well. So thank you very much, and have a great stay at the summit.